Welcome all. So, we will continue with our multiple degree of freedom system analysis subject to impact loading. Last time we looked into the introduction of the Hertz law. So, we will continue with the evolution of the Hertz law and we will look into the different parameters. So, continuing with the Hertz law. So, the impact force acting on each of the colliding bodies, okay, if there are two colliding bodies, okay. So, the impact force between the two colliding bodies, okay, and this is the impact force, is given by the mass times the acceleration component, that is the inertial component, okay, and or it can be given when the bodies combine, okay. So, this is the acceleration of the two bodies, okay, and this is the total acceleration of the bodies, okay. So, if we use the initial condition, okay, and if the bodies are moving with an initial velocity of v naught, okay. So, if we put them, we can calculate the maximum compression, okay, which occurs at the instant of 0 velocity, okay. So, we can calculate the maximum compression acting on the two bodies, okay. And from using this maximum component, we can use this relationship to derive the force time relationship, okay. We can derive the contact force time relationship, okay, given by this particular equation, okay. So, this is a very powerful equation which we can directly use, okay, and if you look into this equation, it is based on the initial velocity condition which we know, okay, and it only depends upon the alpha maximum compression that we can calculate, okay. K1 and K2 are the material constants, okay. So, it depends upon the material properties of the two colliding bodies, okay. So, if we know the material properties of the two colliding bodies, if we know the initial velocity, we can calculate the maximum deformation, okay, and from the maximum compression we can calculate the evolution of the contact force time history, okay. So, using this method we can calculate the total contact force that is occurring in the system, okay. So, this is for the phase, okay, where the forces are in contact, where the bodies are in contact, and after that the force becomes 0, okay. So, here using the typical values, okay, we can calculate the Hertz law, okay. So, if we look into the previous equations, what we need the value of v naught, that is the initial velocity that will be given for a system, and we need the values of K1 and K2, okay. So, here we can calculate the values of K1 and K2, okay, and in order to calculate the values of K1 and K2, we will need some internal values, okay. So, these things can be given, okay. So, depending upon what type of bodies are colliding, let us say two spheres of radius r1 and r2 are colliding, okay. So, if we use this table, we can calculate all the properties, okay. So, here we have a sphere r and a massive plane surface, okay. Basically, what it is meaning is that it is giving the shapes of the different colliding bodies, okay, and similarly we can use the extended charts to calculate the contact forces, okay, for other cases also, okay. So, using the Hertz contact law, we can calculate the force time history of the contact force for the different type of colliding bodies, okay, sphere collision, sphere flat surface collision, and other collision also, okay. We can, from this approximations, we can calculate the maximum compression also, and we can calculate the evolution of the contact force over a time also, okay. So, here in this particular example, there is an elastic mass, okay, it is moving with a velocity of v naught and it hits a beam, okay, and the beam is deformed like this, okay. So, using the contact force, we can calculate the Hertz law, okay. From the Hertz law, we have calculated the contact force time history, okay. So, in this particular figure, a representation of the impact of the body is given, and in this particular figure, example has been given in which there is a sphere, okay, of 1 centimeter radius. The radius r here is 1 centimeter, okay, and the steel beam is 1 centimeter cross 1 centimeter, okay, and it is 15.35 centimeters. The length of the beam is given, okay. So, this is steel sphere and the beam is also made up of steel. So, the configuration of the two bodies are given. okay, the mass of this steel sphere is given, okay, and it is moving with a velocity. Okay. So, in this case using the Hertz contact law, okay, the force time history has been calculated. Okay. So, using this simple approximation, okay, using this simple theory, we can calculate the force contact history, we can calculate the maximum displacement, okay, and we can calculate the compression in the beam. Okay. So, any type of impact problem, okay, we can simplify and use the elastic approach and then calculate the forces applied on the system and the deformation occurring in this particular system. Okay. So, using this approximation, we are calculating the different values of the system. Okay. So, continuing with the approach, okay. So, in this approach what is happening is that the approach is the difference of the displacement of the mass W2 and the deflection of the beam at the contact point W1. Okay. So, here we are formulating the problem. Okay. So, the above is converted into an integral equation expressing the contact force as a function of time. Okay. So, we are representing here the contact force as a function of time. So, now if you look this thing closely, it becomes a circular problem. We have to calculate the displacement and we have to calculate the forcing function also. Okay. But in order to calculate the displacement, we need the forcing function, but the evolution of the forcing function we do not know. Okay. So, this becomes a tricky problem. Okay. So, this becomes a circular problem. Okay. So, the eigen frequencies x1 and the frequencies omega 1 are determined from the equation of the free vibration of the beam, and it depends upon the boundary condition. Okay. So, using this table, okay, depending upon the different boundary conditions, we can calculate the mode shapes and the frequency of the system. Okay. So, we can use this table to calculate the different mode shapes and the corresponding frequency of the system. Okay. So, for different boundary conditions, bar free at both ends, simply supported, cantilever, clamped, okay, symmetric elastic springs, okay, all the expressions are given which can be used to calculate the frequency and the mode shape of the particular system. Okay. So, moving ahead. Okay. So, now we have looked into the multiple degree of freedom system analysis, we looked into the free vibration cases, we looked into the cases having damping, and we looked into the cases where we can calculate the response of the system, the deformation of the system and the contact force in the system using the Hertz contact law. Okay. Now, we will look into the application of whatever we have learned, whatever analysis procedure we have learned, we will try to apply with some case study. So, let us look into one case study where what we are dealing with is performance based response evolution of reinforced concrete column subject to the vehicle impact. Okay. So, here we have reinforced concrete columns, okay, they will be subjected to vehicular impact. Performance based response means that we are going to fix what type of performance we are trying to expect. Okay. Either we are expecting elastic only response, we are expecting cracking in the system, okay, we are expressing that the system has crushed, or whether it is going to fail in any other mode. Okay. So, basically what we are trying to do is that we are trying to have multiple limit state function. Okay. So, we will be looking into the multiple limit state function. So, this is the meaning of the term performance based response. Okay. It means that the different response quantities are fixed based on the different limit state that we are going to put for the system. Okay. So, here a new framework is proposed to evaluate the behavior of the reinforced concrete columns subjected to vehicle impact. Okay. So, this particular method focuses on estimating the dynamic shear forces, okay, and it addresses both the demand generated by the impact and capacity of the column to resist it. Okay. So, we are addressing both the demand and the capacity. Okay. So, both this term D and C will be required in order to formulate the limit state function. So, okay, and the quantity that is being used is the shear force. Okay. So, the whole formulation is being done using the shear force. Okay. So, this approach shifts from the traditional collapse based philosophy towards a performance based design, incorporating multiple levels of structural performance under impact. Okay. So, in the traditional sense, what we say is that we assume only one limit state function, okay, that is normally collapse prevention. But in a performance based design, we can assume different limit state function, limit state function 1, limit state function 2, limit state function 3 and so on and so forth. So, this might be the limit state at cracking, this might be the limit state at elastic only response, this might be at yield of steel, this might be at crushing of the concrete. Okay. So, different limit state functions we can formulate. Okay. So, unlike static or quasi static procedure, the methodology employs dynamic analysis more accurately to capture the vehicle structure interaction. Okay. So, whatever we have learned till now, okay, the multiple degree of freedom analysis will apply this to evaluate the response of the system. Okay. The framework is adaptable and can be extended to other structural members including pre-stressed columns, steel columns, beams, as well as other extreme hazard events such as blast or other type of impacts also. Okay. The application supports the design of impact resilient structure. Okay. So, using this analysis, okay, after we are done with the analysis, we can use this analysis to design the impact resistant structures, okay, where depending upon whatever limit state function we are choosing the optimal damage that we can allow in the system, okay, so that the performance objective is made. It means that whatever limit state function we are choosing, okay, that particular performance criteria will be met out here. So, we are looking into the case where the bridges are subjected to this vehicular type of impact. Okay. So, here is some data which justifies the number of occurrence of this type of impact event. Okay. Okay. So, here we are trying to develop the different performance level. Okay. So, we have defined the different performance level. So, the damage description, we are saying that the structure does not see any significant damage. Okay. So, there is insignificant damage. Okay. So, the performance level that we are dealing with this thing is that we are saying that there is fully operational with no damage. Okay. So, this is the performance description. In the second damage description, there is minor spalling of concrete yielding of longitudinal steel. Okay. So, this is the second damage description, and the performance level is the structure is operational with minimum damage. Okay. So, this is the performance level P2. After that, what is going to happen is that significant cracking in the concrete will occur, spiral and the longitudinal bar are exposed and the buckling of bar might occur. Okay. So, this is the state where the P3 limit state has been reached and there is a collapse of the structure. Okay. So, the damage description is the loss of axial load capacity and the longitudinal bar failure. Okay. So, this is the different performance levels. Okay. So, this is the description of the performance level. Okay. So, normally what we do is that in the traditional sense we only deal with this type of performance level. Okay. But now we have broken down into other performance level, and depending upon the usability of the structure we can devise our own performance level. Okay. So, how does the impact affects the concrete? Okay. So, crack is propagating through aggregate. Okay. And it is the crack propagation is through the aggregates and the concrete. Okay. The concrete brittleness increases with the higher loading rates. Okay. What it is saying is that though with the higher rate of loading, okay, though the strength in the concrete and the steel might increase, okay, the brittleness also increases. Okay. So, for at the lower rates we might be seeing higher strains, okay, but at the higher rate of loading the strain value decreases. Okay. Steel strength rises with increased loading rate. Okay. There is an increase in the strength of the steel. Okay. So, this is the rate dependent phenomena. So, this is sigma strain. So, this is the rate dependent phenomena where we have seen that there will be an increase in the strength, okay, but there might be a decrease in the strain also. Okay. So, shear failure becomes dominant under high impact loadings. Okay. So, when we are dealing with the high impact loading, the shear failure becomes the dominant phenomena. Okay. And the plastic hinge forms at the impact point. Okay. What is the plastic hinge formation? What we are saying is that in case of the reinforced concrete, we say that the entire cross section, for the entire cross section, the ultimate the crushing of the concrete, okay, the crushing of the concrete has occurred in the entire cross section. Okay. So, this is the meaning of the term formation of the plastic hinges. So, then we characterize the different impact events. Okay. So, depending upon the weight of the vehicle and the velocity of the vehicle, we have zoned the entire thing into the low, medium or high event. Okay. So, we have taken a combined approach. Okay, we are not just going to categorize using just the velocity or just the mass, but using a combination of both the mass and velocity. Basically what we are trying to say is that we are trying to categorize the kinetic energy into the low or high impact events. Okay. So, depending upon the mass and the velocity, we have characterized this thing into the low, medium or high event. Okay. So, then we combine both this phenomena, the demand side also, the capacity side also, and we determine the performance objective. Basically what we are trying to do here is that we are trying to calculate the limit state function. Okay. So, upon doing that, okay, what we did was we used LS-DYNA. Okay. We used an LS-DYNA that we discussed earlier also in order to simulate the impact event. Okay. And we calculated the displacement, okay, the displacement time history using the LS-DYNA, and we modeled it using a finite element simulation also. Okay. And we matched the displacement and the velocity. Okay. For using any finite element simulation, what we need to do is that we need to first make the geometry of the system. Okay. After that we have made the geometry of the system, we need to discretize the system. Okay. So, LS-DYNA is a commercially available software that we can easily use. Okay. So, first what we will do is that we will make the geometry of the system. After making the geometry, we will discretize the system. Okay. After we have done the discretization of the system, we will give the values of the material and we will give the values of the element formulation. Okay. So, material, if we are using an elastic material and say if it is steel, so we will need the value of the density of the steel, we will need the value of E of the steel, and we will need the nu of steel. Okay. So, the mass density of the steel is 7850 kg per cubic meter, E is 210 GPa and nu equals to let us say 0.3. Okay. So, using these three values we can define the material as elastic steel material. Okay. Element formulation we can use as constant solid formulation. Okay. Then similarly, so if this is the beam, similarly we can model the impactor also. Okay. We can take a spherical impactor or we can take a box type of impactor. Okay. We first make the geometry, then we discretize the geometry, and then again we give the material properties and the element formulation, same as for the beam. Okay. After that we give the boundary condition. Okay. We boundary condition to the beam. Okay. So, we choose these nodes, okay, and we give them as a simply supported conditions. Okay. So, basically in the software what we need to do is that we need to give the restraints x1, x2, x3, theta 1, theta 2, theta 3. Okay. So, a similar format will be there. So, depending upon whatever boundary conditions we are giving, we can give a value of 0 and 1. Okay. Normally 0 means free and 1 is means it is able to move in this direction or vice versa depending upon what software we are using. So, we will give the boundary conditions. Okay. After that we will give a initial velocity to our impactor, okay, and then we will run this simulation for a certain time t. Okay. Let us say we are running this for 5 millisecond. Okay. So, if we run this thing using DYNA software, okay, you will get this type of displacement, okay, and the velocity curves. Okay. So, then we can match this thing with using any experiments, or we can devise our own experiment and we can do our experiments in a simulated fashion also, because doing all these experiments is very tedious. Okay. So, first we validate with any existing experiment and then we do our own simulation. So, we can get the desired quantities, we can get the displacement quantities, we can get the velocity quantities or stress quantities or any other quantities that we need. Okay. So, using the commercial for any software, we use normally LS-DYNA and we can get the simulation. Okay. So, after doing the simulation, after doing the validation, okay, we have done one more validation, okay, where we have taken a real life example and we have shown that our finite element is able to mimic these cases. Okay. So, this type of real life examples you can also take and do it using any commercial software. You can use LS-DYNA also and see whether you are getting a good match. Okay. That will establish the validity of your model, and then you can model your own scenario and take out the response quantities, displacement, stresses, velocity or whatever is required. Okay. So, after that we then took some cases, okay, some real life cases, okay, and we tried to calculate the capacity of the system. Okay. So, static capacity using normal cases we can already calculate, okay, and then we will try to see what happens to this capacity in the impact event. Okay. So, we simulated 2 reinforced columns, okay, and load ratios we kept it using the conventional forms, okay, and then we took the load cases also. Okay. So, real life loading we took using the different trucks. Okay. We used 8000 kg Ford truck, 8 ton Ford truck, 30 ton EVCO truck, 38 ton tractor trailer and 50 ton EVCO truck. Okay. So, we took 2 structures, okay, and we took 6 velocities. Okay. So, a total of 24 simulations we ran. Okay. 4 vehicles, okay, these were the 4 vehicles and the 6 velocity cases. Okay. Okay. And then we plotted the velocity, okay, versus the mass. Okay. So, on the x axis we were plotting the radial velocity, okay, and y axis we were plotting the mass, okay, and on the vertical axis, okay. So, this is the contours of the shear capacity. Okay. So, this shows the variation of the shear capacities. Okay. It means that the shear capacity is dependent, since this is a dynamic event, the shear capacity, the dynamic shear capacity becomes a function of the mass and the velocity also. In turn, in the static case it will be a function of only the component of the system only, but in case of the dynamic part a dynamic magnification factor is also coming up. Okay. So, we plotted the dynamic shear capacities of the system. Okay. So, these are the some of the impact cases that we can see out here. Okay. The system is being impacted by vehicles. Okay. So, these were the different vehicles that we took. Okay. So, 8 ton vehicle, 38 ton vehicle, okay, and big vehicles we took, okay, 30, 50, 8 and 30 tons. Okay. So, these are the 4 vehicles that we took with different velocities. Okay. So, we plotted the response of the RC column. Okay. So, we are plotting here the dynamic shear demand. Okay. So, we evaluated the dynamic capacity also, we evaluated the dynamic demand also. Okay. So, from the finite element simulation we obtained the dynamic demand and the dynamic capacity of the system. Okay. So, what we were able to do is that in this study we were able to propose a performance based framework for analyzing the RC columns under vehicle impact. Okay. So, what we did was we identified the damage level and we linked it to the performance levels. Okay. We used a dynamic analysis approach, okay, because in the dynamic approach, okay, we were able to see the effect of the inertial terms, see the effect of the damping terms, see the effect of the stiffness terms, see the interaction between the forcing function and the system, which is not available in the static or the quasi-static methods. Okay. So, we established the procedure to estimate the dynamic shear for capacity and demands. The finite element model we validated with experiments and the real crashes, okay, and it is implemented to test our framework, and the results show that the capacity and demand vary with the column configuration, vehicle mass and the vehicle velocity. Basically, they are a function of the forcing function and they are a function of the internal configuration of the system also. The dynamic shear demand exceeds static design values. Okay. So, if we are just looking for the static value, okay, so they normally exceed the dynamic shear demand value. Okay. So, what is going to happen is that in most of the cases we will be doing an over design. Okay. So, that is why we need to update the methods. Okay. So, using this finite element software approach, we can accurately model the evaluation and better design the RC impact. Okay. So, this method we can extend and apply it to other cases also, such as blast impact or other scenarios. Okay. So, basically what we did was whatever we have learned, okay, we use this approach in order to do a finite element simulation, calculate the quantities from there and then use it to refine the existing approach. Okay. So, the same approach by using this type of tools, it can be implemented to do the other real life problems also. Okay. So, moving ahead, one more case. Okay. So, what we can also do is that we can evaluate the response of a multiple degree of freedom system, okay, for an explosion vehicle system under impact load. Okay. So, we can model the system, okay, we can model our system as a discretized mass model that we have already discussed. Okay. So, this will be an multi-degree of freedom system of beam. Okay. So, this is the MDOF system approach that we have already learned. Okay. So, we can discretize it, okay, to model our system response. Okay. So, in order to determine the displacement response of a system undergoing force vibration, so there is a forcing function here. Okay. So, this becomes a case of force vibration due to explosive loading. It is essential to first obtain the natural frequencies. Okay. So, the same thing we have used, we calculate the natural frequency and corresponding mode shapes, okay, from the free vibration analysis. So, the solution is in the generalized coordinate obtained by substituting them into the equation of motion under force vibration. So, this is the equation of the motion of an undamped system under free vibration. Okay. So, we made the forcing function as 0, then we calculated the frequencies and the mode shape. Okay. And after that we can also use this equation to calculate the inertia moment. Okay. So, depending upon the different impact events, okay, we can model them under using different approximations, okay, and these approximations we can use them as a forcing function, okay, and we can write down our generalized mass stiffness and the forcing function. Okay. So, what these are going to do is that these are going to uncouple our system. Okay. So, here we will get the uncoupled system, and from the uncoupled system we can calculate the dynamic response of the system. Okay. So, these are the different approximations of our forcing function. Okay. Okay. Again, free vibration displacement of the equivalent single degree of freedom system. Okay. So, here also we are able to calculate the natural frequency of the system and the different vibration modes of the system. Okay. Now, here we are showing one numerical simulation using a fluid solid coupling, okay, and we are using an LS dyna. Okay. So, here a coupled fluid solid simulation is being shown. Okay. So, this way we can apply the multiple degree of freedom system approximation that we have learned. We can apply the finite element simulation using the LS dyna, whatever we have learned, in order to simulate our real life problems. Okay. And again we can calculate the different responses from the simulation, okay, maximum displacements, okay, and we can plot them using different functions. Okay. So, we can use our simulation to solve the real life problems, we can validate with the existing problems. Okay. So, again different type of loading can be used, okay, and different type of configurations can be used. Okay. So, we can do a lot of simulations easily, so that we are able to substitute and see the effect of the system for the different applied cases. Okay. Okay. So, the conclusion, the modeling approach and the analytical method. Okay. So, we can use a multiple degree of freedom system, okay, and we can approximate using an undamped system, okay, and then we can evaluate the forcing functions and we can evaluate the responses, okay, and this will be very much close to the single degree of freedom system approach. Okay. So, also what we can do is that we can use an equivalent MDOF dynamic coefficient method, okay, and we can see and predict the accuracy and the limitations of the model. Okay. So, the multiple degree freedom system method is powerful as compared to the single degree of freedom system, because we are taking into account the other degrees of freedom also, and this model also successfully predicts the response of the other axial positions. Okay. So, there are some limitations to it, and which can again be taken care of as we increase the accuracy of the system. Okay. So, in this way what we have done is that we have used our knowledge of our multiple degree of freedom system, we use the knowledge of our finite element simulation, applied it to the real life examples, validated with the experiments or the real life cases. Then from there we can simulate our own system, we can do a lot of simulations by varying the different parameters and get a response of the systems in case of displacement, velocities, stresses, and we can evaluate and design our system. Okay. So, these are the powerful tools which can be used to deal with the complex structural phenomena such as impact. Okay. So, I will stop here. Please practice them. Good luck. Thank you.